So first of all, we will have a quiz tomorrow, and I would anticipate me asking you something pertaining to polar coordinates, okay? Now that could be anything from, just basic questions about the polar coordinates, or, polar equations and what the graph of said polar equation might in fact look like. I mean, I may even ask you something about, computing the area of a polar region or something, okay? Or the arc length of a polar curve. I mean, those would be fair game for sure, okay? So polar coordinates is kind of the culmination of everything that we were doing in chapter 10. So that's a good place to focus your attention and to make sure you're on top of things there, okay? And I will remind you, okay, so there is a test, and again, I'm just telling you this now so that you don't, have an absolute fit when it happens later. I always in Calc 2, I've just found that this works best by a mile, okay, because I've just seen the outcomes. One thing that I always do is I let the homework kind of drag behind the actual schedule itself. What that does is it forces you to kind of cycle back all the time. And so you're doing new stuff, but then you're doing stuff that's, maybe a week or so behind. And eventually those two things will start to converge as we come toward the end of the semester. The second thing that I always do is I have a test that covers 2 chapters, like the week before finals week. Okay, covers chapters 10 and 11. The reason I do that is I just want to see where you're at with that specific material. But the second thing I'm trying to do is to jumpstart your study for the final, okay, which is a comprehensive exam that includes 8, 9, 10, and 11, and 12, okay? So chapter 12 will actually have, we'll have a couple of sections there, but I won't be testing you on that on the 3rd exam, but it will be on the final. I've just decided that whatever sheer hatred students have for me, as it, when it comes to that 3rd exam, is just, I'm willing to deal with that because I know that it's the best thing for you as you kind of study for the final and whatnot. You end up way better off in the end, for sure, okay? So tomorrow I will ask you something about polar coordinates. Oh, and by the way, remember on the last exam, I didn't ask you anything about power series yet, yes? So that is still something that will be tested eventually, okay? Any questions before we get going? All right, well, hey, let's keep, let's keep talking about vectors a little bit here, okay? And we're gonna make a leap from the 2nd dimension to the 3rd dimension today. But let's go ahead and get started with some of this. Let me make sure I can actually write on this thing. I think I can. Is that working? Yep. All right. Okay. So remember, I was talking about the fact that that physicists enjoy using this notation that involves the I and J standard unit vectors. I being 1 unit of movement in the horizontal direction and none in the vertical direction, and J is 1 unit of movement in the vertical direction only, okay? And you can write any vector, you can convert it from its component form to its linear combination of IJ form. Sometimes you just call that the IJ form of the vector, okay? And physicists will be inclined to kind of use this notation more than this angle bracket component form notation. But you can still see the components. They're just sitting right here, yeah? The first component happens to be sitting next to I, and the second component happens to be sitting next to J. All right? By the way, I mentioned that most of the time I will write I with a little arrow over it and J with a little arrow over it. And also another thing that comes up a fair amount is sometimes you'll put I with a little hat, like an arrow hat on top of it. And same thing with J. Sometimes you'll put J and put a little arrow hat on top of it. That's another way that those are often written. Okay, but they all mean the same thing. Okay. So we said that a vector encapsulates both magnitude and direction. And one thing that's tricky, and it kind of took geometers a little bit of time, especially in the ancient, mathematical realm, particularly the Greeks, when they wanted to describe direction. Think about that. Suppose that we were like a brand new civilization, okay, just created by the creator, and we had to get a handle on something like direction. How would we talk about that? You know what I'm saying? Say, well, I don't know. See that giant tree over there that God told us not to eat of? If I kind of use that as the middle point, maybe if I do a turn in this direction, I mean, you can kind of talk about some weird, like turning things, yes? And it turns out that that's just angle measure, correct? I mean, eventually, kind of talking about an amount of turning evolved in kind of the way we talked about these things into angle measure. But then you always have to have kind of like a starting point for angle measure. And oftentimes we use the positive x-axis to do that. So direction is most often talked about in terms of angle measure. Okay? And this gets us back to some of the things we were talking about with polar coordinates. Okay? So first of all, let's talk about unit vectors in a direction given by an angle. Okay, so given a unit vector that forms an angle of theta radians with the positive x-axis, and remember, the positive x-axis coincides with the so-called polar axis, yes? And therefore, using theta for my angle is not confusing because that angle is going to be the same as it was for the polar coordinates. Okay, what is its component form? So like here's the situation. So in this case, I'm saying that this thing has length 1, right? So this vector v right here has length 1. So that means its terminal point is literally right on the unit circle. Yes. Well, what would the components of that vector be? If that thing has length 1 and it forms an angle of theta with the positive x-axis, what would the components of that vector be? Cosine theta, sine theta. Yeah? That's the definition of cosine and sine, yeah? Okay? So this guy right here, this point would have coordinates cosine theta, sine of theta. And therefore, since this vector is emanating from the origin, the vector itself would have components, the horizontal component cosine theta and the y component, vertical component sine of theta, yeah? The follow-up question we might have is, what if the vector doesn't have length 1? What do I do then? Okay. So in other words, let me kind of erase this and we can kind of talk about this, okay? What if this wasn't a length 1? What if this was not a length or a radius 1 circle, but it was a radius, well, I don't know. Since I actually used little v, okay, which is a little bit confusing. So let me just write that, v like that, okay? Actually, I'm going to use r, okay? Since that already looks like an r, okay? So this thing is radius r, radius r. What would the coordinates of that vector be? Yeah. R cosine theta, R sine theta. So the only difference would be instead of just cosine theta, sine theta, it would be R cosine theta and R sine theta. Yes? That is the only difference. It's like we've just scaled up this or scaled this unit circle by R units. Does that make sense? And therefore we see polar coordinates kind of making an appearance. Yes? We can describe direction of a vector with the angle theta in the polar coordinates. Okay. Any questions on that? All right, let's look at this. So forces with magnitudes of 180 newtons and 275 newtons act on a hook, like, look here, I'm trying to draw this hook. Okay, sorry, guys. This is supposed to be a hook right here. Do you see this? Okay. Okay, act on a hook as shown. The angle between the two forces is 30 degrees. Find the magnitude and direction relative to the horizontal. So we're going to assume that this force right here is horizontal. Okay, is a horizontal force. Okay, of the resultant force. Resultant force. Okay, well, I don't know. Let's call this vector right here U, and let's call this vector V right here. What are the coordinates of V? 0, 275? 275, 0. Okay, and the units of measurement here are actually newtons, yes? It's kind of like, so if I take the length of V, for instance, right, if I computed the length of V here, that would be 275 what? Newtons, okay? All right, so what about U? Well, basically, I mean, what you have to do is imagine this guy kind of sitting on a circle of radius what? This vector has its terminal point sitting on a circle of radius 180. And so it's going to be just like that situation we encountered, yeah? So it'll be R cosine of theta, R sine of theta, yes? So it's going to be 180 cosine of 30 degrees, comma, 180 sine of 30 degrees, okay? Close the angle brackets there. And just to make sure we're all on the same page here, what is the cosine of 30 degrees? Radical 3 over 2. Okay, cosine of 30 degrees is radical 3 over 2. So that means it's going to be 90 radical 3 in the x-coordinate. And what's it going to be in the y-coordinate? What is the sine of 30 degrees? 1/2. 1/2 times 80 is 90. Yeah? So there are the coordinates of this vector. And again, all units are in terms of newtons right now. Yeah? So what is they asked me for the resultant force. That means the sum total force exerted by these two things. The resultant force, F, okay, so let me just say, the resultant force, F, that means I'm going to take these two vectors and do what with them? Add them, okay? So it's going to be U plus V, okay? And by the way, I could think about that as like, as translating V up here, and then the resultant force, because, right, this is V right here. The resultant force is simply going to be the third, the third leg of this triangle. So this is the resultant force, which is U plus V, okay? So the resultant force is basically in that direction if I take the sum total of those two together, okay? And so what we're going to get here is 275 plus 90 square root of 3, comma, 90. There is the resultant force. Okay? But I want the magnitude and direction of the resultant force. How could I have the resultant force as a vector, but how could I get the magnitude and direction? What would I have to do? I have the resultant force, but they're asking me for the magnitude and direction. What do you guys think? Yeah, that's right. So the magnitude, that's going to be the length of F, yes, which is going to be, the square root of this disaster, right? So 275 plus 90 root 3 squared plus 90 squared, yes? Whatever that happens to be, okay? And how would I find, pray tell, how would I find the direction? So that's the magnitude. How would I find the direction? Yeah, so I would use arctangent to handle that, yeah? Direction is going to be, because like the tangent of, okay, if I wanted this angle right here, I don't know, let's call it alpha, okay? Okay, what I would have to do is kind of think about this right triangle right here, okay? And, I would have this x coordinate and this y coordinate right here, okay? And the direction is going to be, right, because tangent of alpha is equal to y over x. Yes, I'm not using theta here. I'm just using alpha because theta, I think of that as being the original 30 degrees. Okay, the direction is going to be the arctangent of y over x. Right, so that's what alpha is. Arctangent of y over x, which in this case is arctangent of, let's see, what's y again? Y is 90 over 275 plus 90 square root of 3. Okay? Okay, that's what the direction is. What does that end up being? Well, what would you expect to be the case with that angle in terms of degrees? Smaller than 30? Yeah? Can somebody compute that? I mean, make sure your calculator is in degree mode to actually get that thing. But what do you get as the arctangent of 90 over 275 plus 90 root 3? If indeed we make sure our calculators are in degree mode as opposed to radian mode, since I'm talking in terms of degrees right now. 11.8 degrees. 11.8 degrees. Okay, and does that kind of make sense? Yeah, I guess so. Yeah. Okay. All right, any questions on that? It's a little bit of physics there, okay? All right, let's move on to the third dimension, shall we? Okay, we're going to talk about space coordinates. And by space, I don't mean outer space, okay? I mean this space that we live in right now, right? So there's a three-dimensional space in general. So talk about space coordinates and vectors in space. That's the subject of section 2 of chapter 11. It's exciting, okay? So you know that we have been exclusively operating in a two-dimensional realm where you had X and Y like this, right? For a long time. Now what we're going to do is we're going to introduce a third dimension. It's going to kind of come at, this is supposed to be coming out of the board at you. Do you understand? It's going to be a Z axis, and like this is kind of going into the board right there. Does that make sense? Yeah? But we're going to kind of rotate this thing around, okay, so that we can more easily grasp what's happening. It turns out like engineers like to write the three-dimensional coordinate axis system the way I just wrote it. They'll kind of write X and Y in the typical calculus, pre-calculus algebra way, and then they'll have Z coming out of the board. But almost everybody else, including physicists, mathematicians, chemists, almost everybody else actually rotates the whole picture so that Z is going straight up and down. Does that make sense? And X and Y are kind of oriented with X coming out of the board and Y kind of parallel to the board. So this is what engineers like to do. Okay, which is fine. But it turns out that most other people do this, okay? So we just say, so what they'll do is they'll put X like this, they'll put Y like this, okay? This is going into the board, and then Z goes up like this. Yeah? Does that kind of make sense? Look at that picture I just drew, yeah? The dot, 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 well, this is going straight down, but the dot, dot, dot means going into the board, okay? So this is what mathematicians tend to do. So this is mathematicians and physicists and other people tend to write things this way. I have seen a few physicists go with the engineering way at times, but yeah, okay. So here's kind of a general picture of the sort of thing that we're dealing with here. This right here, when I label the x-axis, that's like the positive x-axis. This is the positive y-axis. This is the positive z-axis. This is the negative x-axis, negative y-axis, and the negative z-axis, okay? Now, the thing that's kind of interesting is instead of quadrants, we actually have things called octants now, okay? Because do you see that this basically it's going to consist of like a whole bunch of blocks that are infinite, moving in all directions, and they all kind of meet at the origin, okay? So like this room right here where Z, X, and Y are all positive, this is kind of like an infinite room, yeah? You call that the first octant, right? So that's octant number 1, okay? And then if I jump over here, and let me say where, Z and Y are positive, but X is negative, okay? That's like octant 2, okay? Octant 2, okay? And then if I jump over here, okay, to where X and Y are both negative and Z is positive, that's going to be octant 3, okay? And then, I don't know, I'm sort of running out of colors here. Maybe I'll use black. Okay, if I come over here, oh man, I just erased. What in the world is going on here? Okay, so let me refill that thing back in here, okay? The last one is, Z positive, X positive, and Y positive, or at least the last upper one, that's octant 4. And then guess what you do? Well, let me just do this red one right here. If I go X positive, Y positive, and Z negative, that room, that's octant, what do you think? That's octant number 5, yeah? So you go 1, 2, 3, 4, and then you go down below 5, 6, 7, 8, all around like that, okay? So you could just continue in that way, but I'll kind of leave it there for now, okay? Any questions on that? I mean, we'll graph some points and things like that, but but hopefully that kind of makes sense geometrically a little bit. There's 8 octants, and there's basically 8 infinite rooms that all kind of meet at the origin, okay? And they're kind of bounded by these planes. For instance, you have the XY plane, but you also have the YZ plane. And what else do you have? The YZ plane is kind of like the one that goes through the Z and the Y axis, but what else do you have? Yeah, you have the XZ plane. Okay, that sort of includes the X axis and the Z axis. Those 3 planes slice up space into the 8 octants we just were talking about. Okay. The distance formula. Well, the distance between points in 3-dimensional space is given by this little equation. The distance between points in 2-dimensional space just had the first 2 of those summands. And I'm telling you, you can just apply the Pythagorean theorem again and determine that that you get just the third difference in the z coordinates squared. And that will give you the distance between points in 3-dimensional space. Okay. So it's kind of like this. Here, let me try to draw a picture, okay? So suppose this is like x1, x2, or x1, y1, z1. Okay, so let me try to draw this, okay? So this is the point x1, y1, z1, okay? And then what if I had x2, let me do this in a different color, x2, y2, and z2, okay? Okay, up like this. Okay, so this is the point x2, y2, z2. What is the distance between these things? Okay, I want this distance between these two guys. Well, the way you can find it is like this. You can make a little right triangle right here. Okay, so this little right triangle right here. Actually, hang on. That's that picture's messed up. I want to fix it. Okay, so hang on a second. Oh man. Okay, yes. And let me fix this a little bit. I'm screwing everything up now. Okay, so I'm gonna have to fix all of these things. Okay, so this point right. Oops. This point right here. Okay, like that. And now I want my blue thing to come back in here. And now I have to redraw the coordinates of this point. So x1. Okay. Well, okay. So what I want is this right triangle right here. The picture, I had messed up the look of that picture. There's a right triangle right there. Okay. And actually I can drop like this guy right here. I can kind of look at its shadow down here. Do you see that? Yeah. What is the distance? What is this distance right here? Okay, look at this little right triangle right here. What is this distance right here? What would that be? That one I just highlighted right there. What would that be? Yeah, x2 minus x1. You see that? What would this distance be right here? y2 minus y1, exactly. So what would this be right here? What would that be? The square root of x2 minus x1 squared plus y2 minus y1 squared. Do you see? Yeah? Would just be the Pythagorean theorem. And by the way, that's the same thing as this. Yeah? Okay, those are the exact same distance. And what is this guy? Okay, what's the length of this guy right here? Let me use some green right here. What is this distance right here for that side of the triangle? What's that? Z2 minus Z1. Yeah, that's just this distance between these two guys. That's Z2 minus Z1. So if I wanted to find this length between the 2 points, what would I do? Well, I would square the lengths on the sides and then take the square root, yes? But if I square this guy, hello, what's going to happen? What if I square that? What's going to happen? The square root simply goes away, yeah? And so I would add the square of that to the square of Z2 minus Z1, and I would just end up with x2 minus x1 quantity squared. The square root's simply going to go away, plus y2 minus y1 quantity squared, plus z2 minus z1 quantity squared. And what would I have to do to that whole thing to get that length? Take a giant square root, yes? And that's where this formula comes from right here. It's basically just Pythagorean theorem applied 2 times, yeah? And that's how we can discern the distance between these 2 points right here. I think that's kind of a neat little picture, okay? Any questions on that? I think that's kind of neat to think about, but any questions? Yeah. Yeah, that's right. So, I mean, you kind of discern a pattern at this point, right? I mean, for one dimension, obviously it's just x2 minus x1, which is basically x2 minus x1 quantity squared square root, yes? That's basically how you would get the distance in 1 dimension. In 2 dimensions, you just add the difference in the y-coordinate squared under the square root. And you do the same thing in the 3rd dimension. So it stands to reason the same thing would happen in higher dimensions also. Make sense? Okay. I think that's pretty cool. So what's the equation of a sphere in 3-dimensional space? Well, if you have a sphere of radius r centered at the point x0, y0, z0, then basically you just want this. What is this describing right here? This is the set of all points x, y, z. This equation describes a set of all points x, y, z that are at distance. At distance, like what is the distance? Well, if I take the square root of both sides, I would just get r. Do you see what I'm saying? These are at distance r from x0, y0, z0. So it makes sense based on the distance formula that this would be the equation of a sphere, right? By the way, do you guys remember set of all points? What's sort of a mathematical way of saying that? The locus of all points. Remember we talked about that? Right, it's the same thing as the locus of all points, x, y, z, at distance r from that thing. So there is the formula for the equation of a sphere. Right there. All right, that's the standard way of writing an equation of a sphere. Doesn't that look like the equation for a circle, basically? What was the only difference for the equation of a circle? The z term was gone, yeah? Okay, the z term was gone. Midpoint formula. How do I find the midpoint between 2 points in 3-dimensional space? Well, you basically just take the average of the coordinates, yes? So you add the x coordinates and divide by 2, take their average. Same thing with y's, and the same thing with z's, okay? That's the midpoint formula for a line segment connecting x1, x2 to x2, or x1, y1, z1 to x2, y2, z2, okay? Believe it or not, that's a formula that you utilize a lot in 3-dimensional space, okay? Any questions on this so far? Distance formula, gives rise to the equation of a sphere. And this midpoint formula will be useful to us here pretty soon. Here's a problem. Find the equation of a sphere that has points 2, 4, -3, and 6, 2, -1 as endpoints of its diameter. Okay. First of all, okay, so I'm gonna actually try to draw this. Okay, so X, Y, and Z. 2, 4, 2, 4, -3. So 1. Oh man, are you serious? That thing, I switched over to eraser mode. Sorry. Okay. So 2, 4, 1, 2, 3, 4. So I go 2 in the X direction, 4 in the Y direction, -3 in the Z direction. Okay. So 2, 4, -3. So let's go 1, 2, 3. Okay. So here's the point 2, 4, -3. Yes? Okay. Let's use a different color now. 6, 2. All right. So 1, 2, 3, 4, 5, 6, 2. Okay. 6, 2. And then what do I have? -1. Okay. So I'm going to go down 1. Okay, so this thing right here is supposed to be the diameter of our sphere. This point right here, so this is the point, let me actually label it before I do this. So this point is the point 6, 2, -1. Yeah? Yes.
I don't know if we're going to go through things like, if you were looking at a work or something, are you going to care how we make the graph of it? Or are you just going to care as long as, like, you know, you said like the X become this direction and we can go up, or do you want to do it the mathematical way?
Yes, I want you to do it this way.
Okay.
Yes, because I think it's good for you to learn that. Yeah. Okay, so so this right here is supposed to be the diameter of my sphere. Does that make sense? That's supposed to be the diameter of my sphere. So I don't know. Okay, so this sphere is going to go, I guess, like this and like this. Yeah. So the question is, what is the equation of that sphere? Yes? So let me ask you, what is the midpoint? Okay, look, the midpoint between those two things is actually going to be the center of that sphere, correct? So how would I get that midpoint? All right, so that's the center. Center equals the midpoint on the diameter, okay, which is, how would I get it? Wouldn't it be 6 plus 2 over 2, comma, 2 plus 4 over 2, yes? Comma, -1 minus 3, you add those together over 2. So what do I get? 4, 3, -2, yeah? Okay, it's the average of those things, okay? So, so I have the center. What else would I need to write down the equation of the sphere? What else would I need? The radius. Okay. How would I get the radius? Use the distance formula on what, Brett? On those 2 points. But that would be the diameter, yes? So you just have to divide that by 2. Okay, so the radius, right? So the radius here is just this. Okay, so the radius is going to be one half of the distance between the 2 points. Okay? So the radius is going to be one half the square root of the difference in the x coordinates squared. Okay, so 2 minus 6 squared plus 4 minus 2 squared. By the way, does it matter whether I keep these things in order? Whether I do, like if I go, you know, the x coordinates, I'm taking their difference and squaring it. Does it matter if I do the one first and the other second or the other way around? Does that matter? No, because I'm squaring the difference anyways, yes? I'm squaring the difference. So it's 2 minus 6 squared, 4 minus 2 squared, and finally, negative 3 minus negative 1 squared, okay? So my radius is going to be 1/2 square root of 2 minus 6 is negative 4 squared is 16 plus 2 squared is 4 plus negative 3 minus negative 1 is negative 2 squared is 4. All right. So I'm going to get 1/2 square root of 20, which, by the way, I guess I could simplify that a little bit, couldn't I? What's the square root of 20? How could I right, so write it as 4 times 5 square root. So that's going to be 2 square root of 5. Yes. So what does our radius end up being? Huh? Oops. Thank you. Whereas I was just going on and computing. Yeah, 24. Okay, so what is this going to be? 24. Yeah, so what's that going to be then? 4 times 6, yes? So that's the square root of 4 times the square root of 6, which is 2 square root of 6 times 1/2 is square root of 6. And r is equal to the square root of 6. So what's the formula for the equation of this sphere? Remember on the previous slide, I don't know if you can see it there, but it's x minus x0 squared plus y minus y0 squared plus z minus z0 squared equals r squared, yeah? So what would it be? X minus 4 squared plus y minus 3 squared plus z minus negative 2, which is z plus 2 squared equals what? 6. Equals 6. Exactly right. Does that make sense? Hopefully. Okay. And actually, I mean, I have all this stuff in this particular slide, so I'm gonna go ahead and blitz this now. But I mean, you have to admit that's a pretty good picture right there, correct? I mean, all things considered, that turned out okay. Okay. I mean, I'm always nervous about drawing such things, but that turned out okay. Okay, let me. All right, so this thing goes down to here. Yeah. Okay, so that's an interesting little picture. So here, I just wanted to kind of scroll through what I had here. Okay. There's the midpoint, 4, 3, negative 2, just like we had. The radius is distance from the center to one of those points, or half the distance between those things. Okay. So I could have just taken the center thing and computed the distance between the center and that, and I still would have gotten square root of 6, yes? And so the equation of the sphere is given by that, which is exactly what we got. Okay? Any questions on that? Any questions? Okay, we will continue our exploration of space in the context particularly of vectors next time.